Welcome. Let's talk a little horse racing today. Um, this is a follow-up on some of our counting techniques that we've talked about. Maybe it'll help you get a good understanding of why we use permutations and combinations and how they differ. So we're going to consider this horse race with our horse races, conveniently named A, B, C, D, and E. Some horse racing terminology for you. A perfecta bet requires you to choose the first and second place horses in the correct order to win. So if I choose as my perfecta bet CB and the horses come in CB, I'm going to have a chance to win a fair amount of money on that. But if the horses come in B first and C second, that is not a winning ticket. So you have to pick them in exactly the correct order. That is a perfecta bet. It could be called, I guess, a two-fecta, as you'll see in just a moment. A trifecta bet is just like a perfecta bet, except you have to choose the first, second, and third place horses in the correct order. And that typically, I'm certainly no horse racing betting expert, but that typically is a long shot bet that is maybe considered more of just a fun bet. But oftentimes, but particularly if there's one of the lesser predicted to win horses involved in, sometimes that can become quite a bit of money. And then there is a superfecta bet, which could be called a quadfecta bet, where same as a trifecta, same as a perfecta, except now you have to choose four, and that sometimes is a ridiculous sum of money for just a $2 bet. Okay, so that's some terminology on the bets where you have to choose the horses, a number of horses in a set order, which should imply something to you if you've been exposed to combinations and permutations prior to this. Okay, so let's consider a race with 5 horses, and let's just list out all the perfecta bets that could be made. So we certainly want to organize this, and this is a method of what I've referred to in the past as grinding it out, where we just physically list everything and then we count how many there are. And we'll get more sophisticated as we go. So first, let's consider all of the perfecta bets where we suspect A will be the winning horse. And that, of course, is A then B, A then C, A then D, A then E. So if we were just going for what is the raw number of perfecta bets, shouldn't be too hard right now, because if A can be involved as the winner in 4 perfecta bets, B should be able to, C should be able to, D should be able to, E should be able to. So we would expect 5 winners, or five bets with A winning, 5 with B, etc. So excuse me, 4 with A, 4 with B, etc. So 4 times 5, we would expect 20. And again, important thing to note here is that these are separate, different, unique bets. AC, CA, likewise, BD, DB, those are different bets. If you bet BD and the horses finish D then B, you have lost. Okay, so in this case we see it is 5 times 4. Now that oftentimes I would just define as a closet problem. In other words, we're making choices from a group and then we're making choices again from the group. So if I need to choose a horse for a winner, I have 5 choices. And then once I've chosen a horse as the winning horse, I then have 4 choices. And most typically when we're doing counting problems like this, if we use the word and to join selections, that implies multiplication. I'm not choosing a horse to win or a horse to come in second. I'm choosing a horse to win from 5 and a horse to win from the remaining 4. 5 times 4. All right, let's move on. Consider a race with 5 horses again. How many distinct trifecta bets could make? Well, listing these ones might take some time, but if we were paying attention on the last slide, we realize how many choices do we have for our first horse. First place horse, we'd have 5 choices, and we have to pick a second place horse, 4 remaining, and we have to pick a third place horse, 3 remaining. for a total of 60 of these different orderings. How many distinct superfecta? You might have to go back a couple of slides to see this, but superfecta, like a trifecta, requires us to have 4 winning horses, or the first 4 places. So that would be 5 choices for first times 4 times 3 times 2, or 120. So let's just assume there's only 5 horses in this race and they're all equally likely to win, and we just randomly select 4. Our chances of winning that are just 1 in 120. Now imagine if there were 12 horses in the race, and now we're 12 times 11 times 10 times 9. Not such good chances of winning, although we may have some tips or some ideas on which horses have the better chance of finishing near the top. Okay, now still have 5 horses in the race. Here's a new bet. A box bet is like a trifecta. It requires you to choose the first, second, and third place horses. However, the order does not matter, which means that choosing A, B, C is the same as choosing C, A, B. That is the same box bet. So you're just basically saying, I'm going to pick the first 3 horses. Order does not matter. It does not pay as high, of course, as a trifecta bet, but in turn gives you a few more chances to win than the trifecta bet. Okay, so let's consider a race with 5 horses, and let's list all the box bets that could be made. And this isn't really too bad to grind out by hand. If we were just going to stay as alphabetically as possible, we might just go A, B, C, A, B, D, A, B, E, stick with A's, but A, C, D, etc. Let's take a look at those. And maybe somewhat surprisingly, there are only 10. You can take a look at those. And again, organization is a big deal. And as you can see, going vertically here, I have just gone as alphabetically as possible. And I can stay with the A's all the way to there. And you may say, well, there's 6 selections where A is first. Only 3 where B is first, only 1 where C is first. There must be more selections, but don't forget, it doesn't matter whether A is first or not. In other words, I would not list DAE. DAE has already been selected with ADE. So we only have 10 of these, and that's going to be an important number that we're going to consider in just a moment. Okay, so note that there were 60 results in trifecta and just 10 for the box bets. And trifecta order matters, box bets order didn't matter, but otherwise both we're picking 3 from a group of 5. There were 60 ways we could pick 3 from a group of 5 and put them in different orders. There were just 10 ways we could pick a group of 3 from 60 without considering ordering. And the question, this is the biggie on this, why are there exactly 6 times as many trifecta bets? So you may want to consider that. You may want to pause this and give some thought to that. But I'm going to go ahead with the solution now. Let's assume that we select ABC as a box bet. So that is our box right there. How many trifectas does ABC represent? Well, let's list the trifectas that would come from that. ABC, ACB, BAC, BCA, CAB, and CBA. So we get 6 of these for every one of those. So any selection of 3 that would represent a trifecta is equivalent to 6 box bets. And that goes a lot into our discussion of permutations and combinations. Let's consider where this 6 might come from over here. This 6 might come from saying, okay, we've already in our box selected 3. How many ways can we order those? Well, from the letters A, B, C, I have 3 choices for the first one, times 2 choices for the second one, times 1 choice. So there are 6 ways we can do that. So if we understand there's a shortcut to getting trifectas, how many trifectas are there from all 5 horses? There are, whoops, not 6. There are 5 choices for our first place horse, times 4 choices for our second, times 3 choices. That is called a permutation. That is actually permutation, choosing from 5. I'm going to choose 3. That is 5 times 4 times 3. It doesn't stop at 3 because of this 3. It stops at 3 because this is our first choice, second choice, third choice. That's just coincidental. So if we understand that this number, the number of these, the number of box bets is necessarily only 1/6 of our number of permutations, where does the 6 come from? Right here. If we have 60 perfectas, or 5 times 4 times 3 trifectas, excuse me, every group, there's a group of 6 of those that would be implied in each box. And where did the 6 come from? That is 3 times 2 times 1. We could actually list that as 5 factorial. If I put that over 2 factorial, 5 factorial over 2 factorial gives me this. But we also have our 3 factorial, and that 3 factorial is just because the order does not matter. It's this. So there's a little discussion on combinations and permutations, and hope that is helpful to you. Again, our standard formula for permutations. Here's an example. Permutation 10, let's go 4, would be 10 factorial divided by 10 minus 4 factorial, or 10 factorial on 6 factorial, or 10 times 9 times 8 times 7, and 6 on down would be canceled by the denominator. Whereas combination 10-4 is defined as 10 factorial over 10 minus 4 factorial times 4 factorial. So that would be 10 times 9 times 8 times 7. The 6 on down cancels from this term, all on 4 times 3 times 2 times 1. But we might like to think of that as combination 10-4 equals, take that back just for a second, equals permutation 10-4, this guy, divided by 4 factorial. And what is 4 factorial? The number of ways we can put those in order. The 4 factorial is a number of ways we could put those permutations in that group of 4 in order. So we don't want to count that within the combination. So very, very closely related, and that becomes the real challenge on combination permutation points. Does the author of this problem, or does the problem itself, suggest that ordering matters? It's a combination or a permutation when we choose a group from a group. We just have to then decide whether the order of the selections is important. So hope that's helpful to you. There's our list of trifecta bets if you want to go through that. Certainly something that might be worth revisiting. Really important concept to understand the difference between combinations and permutations.